All right, so in this second video, we talk about dimensional analysis. This is basically just converting units from one unit to another. For example, um, if you are given inches, you can change them to centimeters. If you are given miles, you can change them to kilometers, and vice versa. That's what dimensional analysis is. But then dimensional analysis involves a lot of calculations. And for that reason, we are going to look at some important information that we need to know when doing calculations. We are going to start with significant figures. We define what significant figures are, and also go on and describe different situations where you will be required to identify significant figures. So by definition, significant figures are just non-placeholder digits. So what we mean is that the digits are not simply making kind of a decimal place, or just showing you that you are in the hundreds. For example, if we have a digit like this one, 2500, these two zeros are just placeholders. So they are just showing us that we have 2500. That's the purpose of those zeros. But they are not really important to this number. So we can say that those zeros are just placeholders, and therefore they are not significant. So how do we recognize significant figures? So we'll start looking at a series of values and how we can determine how many significant figures the value has. We'll start with this value here. We'll call it A. Here the number is 2528. The descriptor: non-zero digits are always significant. So the value A has all non-zero digits. So we can say that this has 1, 2, 3, 4 significant figures because all the digits are non-zero. What about B? So B has what we call captured zeros. That are zeros in the middle of significant figures are significant. So here we have a significant figure here. We have another significant figure here, because we know that non-zeros are significant. These zeros are captured between these significant figures. So all these zeros are significant. In that case, this number has 1, 2, 3, 4, 5 significant figures. Let's look at C. Zeros at the end of a number and after a decimal point are significant. So here we have a number 1, and we have a decimal point here. These zeros here are significant. They are significant because we have a number here, and then we also have a point. So if we did not have a point, it would be a different case. But we have a number at the beginning, and we have a point in between, and all the zeros after that point are significant. But because this one is significant and these zeros are also significant, this zero here is captured between two significant sides. This side is significant, this side is significant, this zero captured, which means this zero is also significant. So we are saying here, all these are significant figures. As a result, this number has 5 significant figures. So we are saying zeros at the end of a number and after a decimal point are significant. Let's go to D. Trailing zeros are significant only if the number contains a decimal point, which means if the number does not contain a decimal point, trailing zeros are not significant. So we don't have a decimal point in this number, which means these two are not significant. So the two zeros are not significant. As a result, this number has 3 significant figures. We are not counting the trailing zeros. Leading zeros are not significant. Leading zeros are the zeros at the beginning of a number before and after the decimal point. So you can see here this 0 is before the decimal point and there is no number this side. So this 0 is before decimal point and these zeros are after decimal points before any significant digit. So we call them leading zeros. Leading zeros are not significant, which means this value E, has 2 significant figures based on 2 and 3. F. So we are saying zeros to the right of a number are significant when there is a decimal point at the end. So here you can see there is a decimal point here. There's a decimal point at the end and we have a number and we have these 2 zeros to the right, which means this number is significant, this 0 is significant, and this 0 is also significant. As a result, the whole number has 3 significant figures. Exact numbers, that is here, exact numbers, for example, counting numbers. If you say 2 people, 3 people, 5 people, those are exact numbers. Those types of numbers are infinitely significant. So we really don't talk much about. We can't say report the number of people to 3 significant figures. We cannot say that. Or you can say report the number of cows to 2 significant figures. That's impossible because those are counted as exact numbers. If you say 1, it is 1. It can't be 1.5 cows or 1.2 cows. it can't be that. So those numbers, we really don't focus on the significance of those numbers. We just ignore them. So what we are saying is these counting numbers, we call them accurate counting of discrete objects. So 2 people, 3 cows, 4 peaches. But we also have what we call defined quantities. These are also ignored. We don't talk about their significance. For example, if we say 100 centimeters make 1 meter, we cannot say, oh, here 1 meter has one significant figure and 100 centimeter also has one significant figure. No, we just ignore them because 100 centimeter means is equal to 1 meter can mean a lot of things. It can mean 100.000 is equal to 1.000 infinite. So we really don't focus on their significance. We just ignore them. 12 eggs is equal to 1 dozen. This is also a definition of something. 1 mile is equal to 1.609 kilometers. Those are defined quantities. We really don't focus on their significance. Then we also talk about integral numbers. So numbers that are part of an equation, we don't focus on their significance. For example, radius is pi divided by 2. So we don't say 2 is to one significant figure. Pi is, I mean, we can't know what is the significant figures of pi. So for integral numbers, numbers that are in formulas, we really don't focus on their significance. Volume is equal to 4.4 divided by 3 r cube. We don't focus on their significance because they are integral numbers. So let's look at an example and see how we can apply the information that we have just learned. Determine the number of significant figures in the following values. Now, when you are looking at these numbers, think about the rules that we have just learned. So for the first problem, we have 2 trailing zeros. So these zeros are not significant. So only the numbers 1, 2, 3, 4, 5. So 5 numbers there or 5 digits are significant. So this value has 5 significant figures. So I'll just say 5SF. SF standing for significant figures. So these are not trailing zeros as such. These are leading zeros, not trailing zeros. So leading zeros. So number 2, 300. So because we don't have a point on number 2, we don't have a decimal point, these ones are trailing zeros. So trailing zeros are not significant, which means this value has 1 significant figure. This should be number 3, not number 2. So number 3 has a point here. So number 3 has a point here. It tells us that, yeah, number 3 has 3 significant figures because of the presence of this point here. So 1, 2, 3. So this one has 3 significant figures. That's how you practice dealing with these problems. So let's move on. Now, I will just briefly talk about when writing down values in science, in chemistry, or any other mathematical science class. Sometimes you have very big values, other times you have very small values, and you want to present them in such a way that you can conveniently use the values. For that, we use what we call scientific notation, also called exponential notation. So let us take note of this. So an exponential is a number. So you are given a number between 1 and 10, not including 10. So we'll say a value between 1 to 9, not including 10. And then when you get that value, then you multiply it by 10 and an exponent. So this a is an exponent. So a is the power of 10 of that number, or an exponent. For example, if you have a value 625,000, this is a big value. We want to present it in standard form. This number is a big positive. If we want to write this number in standard form, first we need to have a number, a value that is between 1 and 9, within 1 and 9, and make it our standard. So in this case, if we write the number 625,000, the number between 1 and 9 is just the 6. So we'll take our 6 as the number between 1 and 9, and then we'll put a point after that number. So I'll put a point here, and then I say, how did I get to that point? I got to that point beginning from here. I'm moving from here to here. Initially the point was here, so it moved to this part. It moved again to here. It moved again. Yeah, it's just messing me up. To here. It moved to here. It moved to here. So if you look at how many times has the point moved. So the point has moved 1, 2, 3, 4, 5 times. So I'll say my number is 6.25000 times 10. And since the point has moved to the left 5 times, I'll have a 5 here. So when the decimal point moves to the left, we have positive exponent. So what we are saying, if you want to write it now to three significant figures, then this will be our answer. We may ignore the zeros. The same thing with this number. So if I write the number again, 0.0000258. So the question is, I want to set up this number so that I have a number between 1 and 10, not including 10. Which means my point will be here, between 2 and 5. And then I'll say, how many times have I moved the decimal point? So 1, 2, 3, 4, 5. So I have moved the decimal point 5 times, but I have moved it to the right. So what in the end, what I'm going to have is 2.5, 8 times 10 to the power negative 5. The reason is because I have moved the decimal point to the right. So when the decimal moves to the right, this implies negative exponent. So let us take note of that. You will be required to write values in scientific notation. All right, let's move on. We talked about the SI units, base units. We talked about those units. But sometimes we have units that are bigger than the base SI units. For example, if you have like 1 million kilometers, I mean, you don't want to report 1 million kilometers because that is too much. You want to use, or if you have 1 million meters, you don't want to report 1 million meters. That is kind of too much. So you need to use another unit. So let's say I have 1 million meters. And I'm saying, nope, I don't want to do that because it's a big number and it's inconvenient. I can just say, oh, this is 1 mega meter. So given as 1 big M, small m. So this number here, this value here is more convenient than this value. So because of that, we usually use prefix multipliers to make the values more convenient to use and more convenient to read. So the prefixes that we have are, you just need to study this table. A giga is 10 to the 9. And here we have the symbol for that. So this column is for symbols. This column is for the prefixes. This column is for the symbols. This column is for the multipliers that we multiply our unit. So a kilo is 10 to the power 3. Actually, the units that we'll focus much with in this class are the kilo, the mil, the nano. These are very important units that we are going to focus on. A little bit of micro, a little bit of micro. So what does it say? A micrometer. This one is telling us that 1 micrometer is equal to 1 times 10 to the power 6 meters. So instead of using this is too cumbersome. You can just report it as this. So please study this, especially study this table. It is very important. Examples that you can write using the table. So write the following expression in scientific form without prefix multipliers. So when I say without prefix multipliers, I mean you should use the base SI unit. For example, I want you to change this nanometer to meters. I want you to change this mega. So this is mega. I want you to change this megagram to grams. That's what I mean. If I say I want you to write this without prefix multipliers, because a nanometer is a prefix multiplier, a megagram is a prefix multiplier. The actual base for a nanometer is a meter. The actual base for a milligram is a gram. So how do you write these expressions? You go back to this table. It will tell you what you have multiplied to move from a meter to a nanometer, or from a nanometer to a meter. So let me call this one A, this one B, and then draw a line here. So for A, I will say 1 meter is equal to 10 to the 9 nanometers. That is one way of saying that. Or in other words, you can say that 1 nanometer is equal to 10 to the negative 9 meters. But you know what? I don't like using negatives. If the small value here, if the small value is given a 1, the bigger value is going to have a negative. For example, a nanometer is smaller than a meter. If you give a 1 to the nanometer, definitely the meter will have negative exponent. But if you give the value 1 to the bigger measurement, like if you give 1 to the meter, it means the nanometer will have a positive exponent. So we need to take note of that. So really, this one is correct, but I don't like using it. I like having positive exponents instead of negative exponents. So solving this one, I would say, yeah, I have 250 nanometers. 250 nanometer, I will start with saying 1 meter is equal to 10 to the power 9 nanometers. Then I want to convert from nanometer to meter. What I'm going to do is I will just write this nanometer here, 250 nanometer, and then multiply. So because I have a nanometer here, I am using this information. 1 meter is equal to 10 to the 9 nanometer. I have a nanometer here. I'm going to put a nanometer down here, which means at the top, I will put a meter. I will learn more when we deal with conversion factors. But for now, this is what I want you to follow. So because there is this nanometer here, will cancel with the nanometer above there. This nanometer goes with 10 to the 9. So I'll put 10 to the 9 here. This meter goes with 1, and I'll put 1 here. When I multiply those, I get the answer is 2.50 times 10 to the power negative 7 meters, because I want the answer to 3 significant figures. So that's how I convert from the nanometer to meter. For B, I'll do the same thing. I'll write my value here, but before that, I'll say 1 megagram is equal to 10 to the 6 grams. If we go back here, the mega is here. So 1 megagram is equal to 10 to the 6 grams. Following that, then I'll write this value. So 4500 megagram, and then the multiplication sign, a line here. Because there is megagram here, I'm gonna put megagram down here, and then gram up here. But gram goes with 10 to the 6, so I put 10 to the 6 with the gram here. Megagram goes with 1. Then I just multiply the two, and I want my answer to 3 significant figures. So I get 4.50 times 10 to the 9 grams as my answer. So that's how we can convert units from a bigger or from a smaller unit to a bigger unit, or from a bigger unit to a smaller unit. So let's move on. Now, we have talked about significant figures, and we have talked about the rules that we use to determine significant figures. But how do we use significant figures in our calculations? If you are multiplying or dividing, your answer is based on the number of significant figures. actually is based on the value that has the smallest significant figures in your multiplication. So value that has smallest number of significant figures in your calculation. So your answer will be based on that value. If you are adding or subtracting, your value depends on decimal points or decimal places. So your answer will depend on the value that has smallest number of decimal places. We are going to see what we mean by that. Let me show you examples. So this A and B. A is multiplication and division, and B is just addition. So we are saying the answer we get here depends on the smallest. The answer we get here, the number of significant figures for the answer will depend on the smallest significant figure in this calculation. So let's see. 8.567. This one has 4 significant figures times 1.4. 1.4 has 2 significant figures. Divided by 2.35. 2.35 has 3 significant figures. Now, the smallest number of significant figures is from 1.4, which means when we make our calculation, our answer must have 2 significant figures. So after my calculation, I find that the answer for this one is 5.1. That is to 2 significant figures based on this value. We have done this because when multiplying and dividing, our answer is based on the number of significant figures in our answer. Is based on the smallest, or is based on the number with the smallest significant figures from the calculation itself. Now, when adding, that is here, when adding, our answer must have the number of decimal points as the value with the smallest decimal point. In this case, if we look at this one, has really the biggest number of decimal points, followed by these two. The smallest number of decimal points is here, 0.11. That is 2 decimal points. So this one has 2 decimal points. This one has 3. This one has 3. This one has 5. So our answer is going to have 2 decimal points. And if you add everything on this one, the answer will be 32.33. That is to 2 decimal points. So in summary, multiplication, division, use significant figures. Addition and subtraction, use decimal points. So we need to take note of that. Let's move on to something else. When making your calculations, I can ask you to round up or round off your answers to two significant figures or two decimal points. So the rule is, if you want to round off an answer, avoid rounding intermediates. You need to round up the final answer. For example, if I say I want my answer to three significant figures, in your calculations, try to have as many significant figures for your values as possible. And then you round only the final answer. For example, here I had my figures here, this figure, this value, this value. I didn't mess up with their significant figures. I calculated, I get this long answer, and then I decided to round it to two significant figures. I get 0.082. So what happens if I decide to round off this problem here? I'm going to have 23 instead of 22.528 over 275.15. And then I get 0.084. 0.084 is not equal to 0.082. You can see they are different. When I did not round off, I get 0.082. When I round off the answer, I get 0.084, which is a different answer. So when rounding off your answers, make sure that you round the final answer. Don't round before the final answer. If you have to round before the final answer out of convenience, try to keep as many significant figures as possible so that you do not affect your final answer. All right, so let's move on to the real substance, unit conversion. What is this unit conversion? It's just changing a unit, changing one unit to another unit using what we call conversion factors. Normally, you have a starting quantity, the quantity that you are given, times the conversion factor to give you a new dimension or a new unit. So starting unit times conversion factor to give you a new unit. We are going to look at examples that will give us an idea what this is. So suppose you want to order a bicycle with a 25.5-inch frame, but maybe you are in a different country where the information is given in centimeters, and then you are thinking, I know inches, but these are centimeters. How do I know the actual inches that I want from these centimeters? What size should I order? So we know that in terms of conversion, if we go back here, we have a starting quantity times conversion factor to give us equivalent quantity, which means you need to know the conversion factor. that you are going to use. In our case, 1 inch, 1 inch is equal to 2.54 centimeter. So that is our conversion factor. Now, the way I solve these problems, I will write my starting quantity. So this is the starting quantity, 25.5 inch. So I'm going to write it here, 25.5 inch, and then multiply. Since I have an inch here, I need to put an inch down here so that the inches are going to cancel. So this inch has taken care of this one. Then it means at the top, I am going to put a centimeter. Now this is taking me from inches to centimeters. The inches go with 1 and the centimeters go with 2.54. Then my answer is 64.77 centimeter. But now, because this is multiplication, I need to look at what is the smallest significant figures from my calculation. So this value has 3 significant figures. I am not using this value here because it's a like a defined quantity. As a reminder, we say if you have like 100 centimeters is equal to 1 meter, you ignore significant figures. This is the same case here with this one. We can't use significant figures of this one because it's a defined quantity. So the answer for this one will be to 3 significant figures. So this is the actual rounded answer. Now, what we are saying is I am going to order a bike that is 64.8 centimeters because I know that 64.8 centimeters is equal to 25.5 inches. Let's look at another example. The speed limit in many highways in the US is 55 miles per hour. What is this speed in kilometers per hour? So here we are already given a conversion factor. This one is a CF. This one is our starting quantity. So what I do, I'll just start here, 55 miles per hour. And then I want to get rid of miles here. I'll put mile down here so that the miles cancel. And then kilometers up here. The mile goes with 1. The kilometer goes with 1.60 After my calculation, I get 88 kilometer. That is two significant figure coming from this. So the mile cancels with mile here. The kilometer goes 88 kilometers per hour. Let's look at another problem. So you may have multiple conversion factors. You have a single starting quantity, like we can see here, and then conversion factor 1, conversion factor 2 to give you equivalent quantity. So an example here, a Japanese car is advertised as having a gas mileage of 15 kilometers per liter. Convert this rating to miles per gallon. So here you are given two conversion factors. 1 mile is equal to 1.609 kilometers. 1 US gallon is equal to 3.785 liters. These are the two conversion factors. So to create space, I'll just write these ones again here. The same question, conversion factor 1, conversion factor 2. This one is your starting quantity. This is your starting quantity. It's just messing me up. So I'm going to start with that quantity, 15 kilometer. Sometimes it's good to, per liter is the same as per 1 liter. So I'll say 15 kilometers per 1 liter. Now I'll put conversion factor 1 here, then conversion factor 2. Then I'll say what units do I put between these two lines. I have a kilometer here. I'll need to put a kilometer down here so that the kilometers will cancel. Then I go to this conversion factor and say this part is a kilometer. After this kilometer, what is next? The next one is mile because it's in the same conversion factor. So I'll put a mile above here. And I'm done with the kilometer mile conversion factor. Then I'll go next. What else do I need to cancel? I need to cancel the liter, which is given here. So the liter is down here. I'm going to put the liter up here. This liter goes with which conversion? It goes with the gallon. So I put the gallon down here. After doing that, then I put the values. The kilometer goes with 1.609. The mile goes with 1. The US gallon here goes with 1. The liter goes with 3.785. Now, after all my calculations, and my answer actually should be to two significant figures, I find 35 miles per gallon. That's how I solve this problem. So you can see that here, this one is conversion factor 1. Let me just delete this part. So this one is conversion factor 1. This one is conversion factor 2. Let me look at another problem. Convert 36 kilometers per hour to meters per second. So for a problem like this one, I am moving from kilometers to meters. So for that one, I'll say 1 kilometer is equal to 10 to the power 3 meter. That is the first conversion. Then I'm moving from hour to seconds. And 1 hour is equal to 3600 seconds. That's the second conversion factor. This one is my starting quantity. So I will start with that. 36 kilometers, 1 hour times the first line, because I have two conversion factors, times the second line. So I want to cancel kilometers here, which means I need to put kilometers down here. Kilometers go with meter. I want to cancel the hour here, which means I need to put hour up there. And then the hour goes with seconds. Then I'll start just putting the numbers. The seconds go with 3600. The hour goes with 1. The kilometer goes with 1. The meter goes with 10 to the 3. After all my calculation, I want my answer to be to two significant figures. I'm going to have 10 point meters per second. That's how I solve this problem. Let me see if I can quickly solve two more problems, maybe within 10 minutes, and see how it works. So these are a little bit more complicated, and when you look at them, I want to teach you how to navigate problems like this. So this is an acetaminophen suspension for infants. Contains 8 milligrams per 0.80. If you see something like this one, this is conversion factor 1. You are already given a conversion factor there. The recommended dose is 15 milligram per kilogram. This one is conversion factor 2. So what is your given quantity? For you to know your given quantity, follow the statement that has the actual question. So the actual question is, how many milliliters of this suspension should be given to an infant weighing 14 pounds. This one is your starting quantity. Why is it starting quantity? Because it is with the question that you want to determine. So I'm going to start with 14 pounds. And remember, I have two conversion factors. So this is my first conversion factor. This is my second conversion factor. Actually, I have a third conversion factor which is implicit where I need to convert a pound to kilogram. Because how many milliliters of this suspension should be given to an infant weighing 14 pounds? These two conversion factors don't have pounds. So I need to find a way to convert pound to kilogram or to convert kilograms to pounds. So here I'm starting with pounds. I'll go with a pound here, but I'm converting the pound to kilogram. But kilogram should go with kilogram. The aim is to cancel the units. So kilogram here goes with kilogram down here. Where does the kilogram come from? It comes from this conversion factor. So after kilogram here, we have a milligram. So you need to take a milligram up here. If you have a milligram up here, you need to have a milligram down here. Now we look at this conversion factor. This is a milligram. A milligram goes with a milliliter. So you put a milliliter up here. So the rest is just putting the numbers. The milligram down here goes with 80. The milliliter up here goes with 0.80. The kilogram down here goes with 1 because there is a 1 here which we don't need to show. The milligram up here goes with 15. Conversion from pound to kilogram is 1 kilogram is equal to 2.205 pound. So we are going to put 2.205 pounds here and 1 kilogram here. So the answer to two significant figures is 0.95 milliliters. So we'll need 0.95 milliliters of the suspension. Let's look at the last problem. The price of the euro was recently 1.27 US dollar, and the price of 1 liter of gasoline in France is 1.39 euro. So if you see a problem like this one, look for the conversion factors. Here, the price of the euro, which means 1 euro, is equal to 1.27 US dollar. So that is the first conversion factor. So this is CF1. Conversion factor number 1. Here it says the price of 1 liter of gasoline in France is 1.37. That is conversion factor number 2. 1 liter is equal to 1.39 euro. So we have two conversion factors here. Now, what is our given quantity? In the previous problem, I said for you to find given quantity, you need to go where the actual question is. So the actual question is, what is the price of 1 gallon? This one is your given quantity, or starting your starting quantity. So we already have two conversion factors, but for this problem, we'll need 3 conversion factors. You see why. So I will start with 1 gallon here times. I need to get rid of the gallon. I need to convert from gallon to liters. Then I need to cancel the liter, which means I need to put a liter down here. But now if I have a liter down here, this liter here goes with the euro, which means I put a euro up here. Times down here, I need to put a euro so that the euros cancel. This euro goes with the dollar. And then I put a dollar here. Then I just put numbers. So the conversion from gallon to liters, 1 gallon is equal to 3.785 liter. So for this one, we have a 1 here, 3.785 up here. For the euro or for the liter, we have 1 liter here, but we say this liter goes with this euro, 1.39 euros. And the euro, 1 euro goes with $1.27. And then our answer is $6.69. So that's how we solve a little bit more complicated conversion factors problems. All right, so make sure that you have completed your video assignment with these 2 videos. In class, I'll just talk a little bit about conversion of temperature units. Thank you.